Okay, so where was I? Informal, yeah, informal. um, yeah, I'm going to talk about myself, a little bit about my background, and then more about ThoughtWired, the company that I co-founded and have been working on for the past 6 years or so. And then I'll just kind of give a brief overview of what we do and kind of the journey that we've been on. And then I'll let you guys kind of drive where I go into more detail, because I really don't know what you want to know more about, what interests you. I don't really mind talking about anything. And then at the end, I'll do a brief run through of our software and a little demo that you guys are all free to try as well. So make sure that there's time for that. How much time is there?
It's an hour.
An hour. So till 1:30? Okay. Okay. So yeah, my background is in engineering. I did Mechatronics Engineering as my undergraduate at the University of Auckland. And then I did a PhD in Biomedical Engineering, which was around researching how to look at muscle signals, so EMG signals, the electrical activity in muscle, and use that to control exoskeletons or prosthetics. So I built an interface that measured those signals, did a little bit of signal processing around it, converted it into a joint motion, and use that to reconstruct where the arm would be if there was an arm there. So imagine if you didn't have a forearm, you could measure the electrical activity from your bicep and your tricep and use that to recreate that movement. And then if you put a prosthesis there, you could use that signal to then drive that prosthesis as if the arm was there. And so that was kind of what my research was around. There were two kind of case studies around it. I did one for the elbow joint, which is the simplest joint in the body. And I did one for the jaw, so the masticatory system, which is a lot more complex because there's 6 degrees of freedom of movement, which means it can move translationally, rotate, twist, that kind of thing. It's actually quite a complex system, and the joint that allows it to do that is really complex and prone to disease and injury. And so this kind of research was kind of around how to build an exoskeleton to help rehabilitate it and to assist in doing, which sounds impractical and is, but it's what they got funding for. So that's how university works. After that, I spent about another year and a half as a postdoc doing kind of psychology-related stuff around Alzheimer's and looking at the brain signals, so the electrical activity in the brain when people are presented with facial stimuli. So if you get shown a picture of a face, there's a particular spike that happens in your brain. And my work was focused around trying to figure out whether that spike meant you recognized that face or if you didn't. And the application of that was in what's called reminiscence therapy, where people with Alzheimer's go through like a talking exercise. They get shown stimuli, they kind of try and relive past memories and see, and therapists use that to kind of gauge how much they've forgotten, that kind of thing. And the idea of this was to have a objective way of figuring out whether a person actually recognized a face or not, as opposed to leaving it up to them to say yes or no, which sometimes they can lie about. So that was my postdoc. And after that, I went on to ThoughtWired full-time, which started in 2012. So sort of halfway through my PhD, I started doing this, mainly out of boredom, because working at university for like 6 years is pretty boring. It gets really tedious, and so I was looking for other things to do. And I saw that Dimitri, my co-founder and current CEO, was looking for a team to enter Spark Velocity, which is the University of Auckland's business plan competition. And so I got in touch with him and we decided to form a team. And so we entered the student competition with an idea around using consumer-grade brain devices like these, which measure the electrical activity in the brain, in the application of providing people with severe physical disability a way of communicating. And so the target population is people who can't talk and cannot move well enough to use an existing interface. So by an interface, I mean anything that you use to interact with technology, whether that's a keyboard, a mouse, a touch screen, a speech system. There are other assistive devices like sip and puff systems. I don't know if you've seen that, but it's a tube that you blow air in and out of. You have things like bite switches, which you just bite down on. Stephen Hawking used a infrared camera that detected muscle twitches in his cheek. So he would just twitch his cheek, and that's how he communicated. So there's heaps of devices like that, but there are still people who lack the capacity or the control to use them. And so this is kind of where this came in that it doesn't require any physical ability at all. It just requires no cognitive impairment. So as long as you can think and have an understanding of, or natural understanding of language, and kind of are aware of what's going on, in theory, you should be able to use something like this to achieve an action, and from that action, then do things. So that was kind of the idea around it. And so we formed a team with Dimitri, who's more of a business information systems background, myself with engineering, and Savnaz, who is a health psychologist, and Konstantin, who has experience in entrepreneurship and international business. And we entered Spark. We did pretty well, and we got some seed funding from that. We then went on to do Microsoft's Imagine Cup, which is a more technology-driven competition as opposed to the commercialization side of things. We also did quite well in that, and got more capital. And kind of at that point, we were thinking maybe we're onto something. People kind of didn't believe that the technology would work, or they would think it was kind of too sci-fi to be real. But when we did demos and stuff and they could see that it actually did do what we said, then they kind of changed their minds. And so that was quite reassuring. And so we continued doing it for, what was it, like 3 years part-time-ish? We were using mostly the capital that we gained to help fund development. So what we build is mostly software. These devices are off the shelf. We don't make the hardware. We've thought about going into hardware, but it's everyone we've asked about whether we should go into hardware say, don't go into hardware. So we've taken that on board and haven't really taken the leap yet, but we really want to, just because of the limitations behind it. So a bit about the technology. It relies on a principle or signal called electroencephalography, which is kind of like, I guess, ECG or EKG. I don't know if you've ever seen on TV, like when you have a heart rate monitor, there's a little electrical impulse that beeps every time your heart beats. So it's a very similar principle, except on the brain. And the main difference is that because it's in the brain, it's a much smaller signal. So you're dealing with microvolt amplitudes, whereas with the heart, it's kind of millivolt up to tens of millivolts, which is 1,000 times bigger, so much easier to detect. And this signal has been used in research for more than half a century in sort of psych labs, understanding how the brain works, how neurons fire. But the main difference is that the equipment used to do that kind of research uses these really big neural nets, which have like hundreds of electrodes and measure the activity all around the brain, and cost up to 120K, which is quite expensive. Most people wouldn't be able to buy one of those and use it in their homes on a daily basis. And so this is $200. So when you think about that kind of step from research-grade equipment to something of this form factor and that decrease in price, it was kind of one of the, catalysts of us thinking about this, and that this technology is now becoming way more accessible. And so this came out in 2009-ish, I think, or maybe earlier 2007. But the whole kind of process of taking this research-grade technology and making it accessible to consumers was a huge leap. Now the problem is that the reason why it costs 120K is because there's a lot of fine-tuned electronics in that system. There's a lot of noise with this signal. Because it's a very low electrical signal, you pick up electrical noise interference, you get artifacts from movement, from your muscle activity, from all the sorts of electrical things going around. And so in order to get a good signal out, you need to have really finely tuned filters and good signal processing techniques and algorithms. And so in these devices, that's not so great. And that's the trade-off. And so in order to then use it for control, we have to build a whole bunch of other sort of smarts into it to kind of deal with that. That's kind of mostly what we've been trying to work on and solve over the past 3 years, is how to make it so that it is, firstly, easy to use, secondly, reliable, and robust. That's the main issue. The one about being easy to use is also really important because you're taking quite a sophisticated technology and putting it in the hands of people who don't or aren't familiar or even afraid of technology. And so making it or putting it into a form and providing materials that support its use is really important, making sure that they understand how to use it, and if anything goes wrong, how to fix it or troubleshoot it. And that's kind of really been the main learning experience for us, is figuring out what those problems are, because no one's done it before. There isn't a...
Is the meetup?
Yes.
Yeah, go ahead. No, go away. The main thing that we have had to learn and deal with is around the difficulties with these devices themselves. So for example, this is an off-the-shelf headset. It is made with no particular use case in mind. The company just made them and were like, go free, do whatever you want with them. And so when you look at it, it's a rigid device. It's adjustable. You can adjust the size of it, so that's cool. But then the rest of it is like rigid, hard plastic, right? And it goes on your head like this. Okay, and this is a reference electrode that goes on your earlobe, and that's pretty much it. Now, when you first put it on, it feels okay, but after about 10 minutes, you get to start feeling a throb in here, and you get to sore here as well. So, in terms of a comfort device, it's crap. You can't wear it for more than 15 minutes, and that defeats the whole purpose if you were to try and use it as a tool for communication. And this is just one of them, but it's the one that we're still using because it's the best that we have so far, which is quite sad. But yeah, so plagued with problems like that is basically what we've gone through. We initially started off using a headset called the Emotive Epoch, which has more electrodes, but looks like a sort of like a web of electrodes on your head. But the problem with that was it had felt electrodes. So this is a metal dry electrode, just basically a metal plate. But the felt electrodes you have to moisten with saline solution to get a good electrical skin contact good contact between the skin and the electrode. The problem with it is that it dried out every 15 minutes. So every time we put it on, we have to adjust it. You have to deal with getting the electrodes through the hair onto the scalp, make sure there's a good connection. And then after 15 minutes, it'll dry out, and you have to do the whole process again. Now, the thing about that is if you're a caregiver or a person who looks after someone with a disability, you need to do that for them, right? Because they can't do it themselves. If you have to do that every 4 times an hour, it's a lot of effort, it's a lot of work. You're already doing a lot for that individual in terms of full-time care and meeting their needs. You're not going to do it. So what happens is that it just won't be used. And that's a common problem with assistive technology, is that people get too frustrated to use it. The abandonment rate is something like 70%, which is high. And it's mostly around poor usability design. And so our whole kind of approach has been around making sure that we design it with those kind of ideas in mind, and using a user-centered approach or co-design approaches where we make sure that the people who are using it have as much input and say in the design process as possible. So we go through an iterative process where we have a UX team, user experience team who kind of go through people's needs, various stakeholders' needs, whether it's a therapist, a caregiver, the actual individual who'll be using it, collects information and gets the information out of them, turns that into, I guess, user stories or requirements in terms of what the product should look like, and then that gets passed on to the dev team who then convert that into technical specifications and build it. And we do that iteratively as often as we can, and then run trials once it's done to test it out, make sure it meets their needs, get feedback on it, and then go through the cycle again. And that's kind of how we've been trying to do it, but getting a lot better at doing it now, because all of us were kind of fresh out of uni when we started. And so we didn't really have any experience, and so kind of had to discover or figure out how to put all these processes into place ourselves, which has been a learning experience, but over time has gotten a lot smoother and faster, and that's really good to see. So quite early on we had a lot of failure. We would build something and it wouldn't work for some reason or another, and we had to come back and reassess why and figure out a way to solve it. And so the hardest part, I guess, was kind of when we ran out of money, and we needed to start raising, and that kind of then increased the stakes around what we were building, and we were getting actual investors involved. We first did a round with friends and family. It's usually called the friends, family, and fools round. So people who are okay with giving you money and not necessarily interested in a return on investment. And so we did a small round of that. That got us through a little tough spot. And then I think, what year was 18? So about two years ago, we did a crowd-funded equity campaign through Pledge Me, where we got, which is basically like Kickstarter or Indiegogo, but instead of buying a product, people invest and get shares. And so we raised quite a bit of money from that, which was enough to keep us alive for another 18 months or so. And then we did an angel round last year, and that just closed off earlier this year. So we will survive for another year or so, and then we'll have to start looking for money again. But yeah, since then we've kind of grown as well. We've now got a cognitive neuroscientist with us, a senior software engineer. We contract out to a couple of designers every now and then, and we've also got a research assistant. So quite a multidisciplinary team, and we're still small enough that we all have many hats and do many things, and so it's quite a varied working environment. We're based out at Hobsonville Point Secondary School, which is really cool for us because A, it gives us a test population, which is quite handy, and secondly, the arrangement with the school is really nice because we get to use space and resources, and in return for that, we don't pay anything, but we give up time to the students. So we run workshops or lessons or help them with projects or whatever, because it's a really self-directed kind of progressive approach to learning, and it's a really cool way for them to interact with industry and learn things that you don't normally learn in a regular school curriculum. So that's really cool. Yeah, so that's kind of a brief overview of where we've been and kind of where we've got into now. We've done a lot of user testing with people with cerebral palsy and motor neuron disease. And so the important thing about the inability to communicate is that it's not disease specific. It's more symptomatic, where it's just the condition that you're in is what's important, not the disease driving it, because with, say, cerebral palsy, you have different scales of severity. And so we constantly work with organizations to try and find people who would be suitable for our technology and trial with them as soon as we can. Yeah, has that kind of been interesting so far? Like relevant to what you want to know about? Is there anything you want me to kind of delve into a little bit deeper or provide more information on specifically?
I've got like a very pressing question that's bugging me. So when
Yep.
I think thoughts, right, I think in English.
Right.
And
How does it work?
In Spanish
Yep.
translate to the same movement or same message?
Okay.
Like, does our brains have a level that says, okay, this is language and this is frequency?
Yep.
And regardless of what language you sent me, I'll translate into frequency.
Okay.
And
So.
you obviously have to translate that into whatever.
Yep.
Right?
So, okay, a brief lesson on neuroscience. Okay, so the brain, the way that the brain works is there's billions of neurons in it, right? And the way that thoughts work are these neurons firing rapidly with little electrical impulses, okay? And everyone thinks differently. So you have areas of the brain where the same kind of thoughts occur, like say, for example, visual processing always is generally at the back of the head. And your motor cortex is a strip across the top, so that's usually consistent across people. And the way that these devices work is they pick up a aggregation of those neurons firing. And so if are most people like engineers or technical here? Yeah, okay. So it's kind of like, it looks like an audio wave where you have peaks and troughs, and it's noisy, and it increases and decreases in frequency depending on the pitch or volume of the sound. It's similar to that in terms of how it looks, and so there's lots of different frequency components in it that you can extract out using filters. You can do time domain, frequency domain analyses, and that kind of thing. And so when you think of anything, it's going to be a almost random combination of different neurons firing, right? And because of that, if you think of, say, an apple, right? When you picture an apple, and you picture an apple again, those aren't going to be the same patterns. They're going to be pretty different. And it's going to be different depending on your current mood, your emotion, whether you're hungry or not, any other things going on in your subconscious. So it's going to be totally different. And so when we say that we're reading brain activity and using it to communicate, we're not actually reading thoughts. You can't think, I am hungry, and our computer will know, oh, you're thinking I am hungry. It doesn't work like that. That's like next level stuff. That's kind of in the future with implanted electrodes. And so the difference is that this is non-invasive. You just stick it on your forehead and that's it. Whereas there are companies around the world like I think Neuralink, Elon Musk's one, and Facebook's doing one, where they're looking at implanting electrodes, so directly putting an electrode array on your brain, and so getting much closer to the neurons and therefore having more resolution in terms of what they're actually measuring. And from there you can potentially get more sophisticated signals or information out of it. An example of that is that they recently were able to show a person pictures or images of different objects, and using the brain data that they collected from this electrode, they trained a machine learning algorithm to reconstruct what those images looked like from that data, which is really interesting. And so what we do is we kind of take a little step back from that level of detail and look at a general state of the brain. And so this is in the frequency domain, where under different conditions you have different waves of activity. So for example, if you close your eyes, you get an increased amount of alpha activity, which I think is between about 4 and 8 hertz. And so when you close your eyes and you look at the signal, you see a little wave, 4 to 8 hertz wave that shows up on the screen. And that's detectable. And that happens across everyone. So that's more of a viable signal that you can turn on and off. The one that we actually use is around attention or focus. And so if you concentrate on something and ignore kind of peripheral thoughts and just think of one thing in particular, your brain enters a certain state that we can pick up on. And so if we can train you to enter that heightened state of focus repeatedly and reliably, and we can detect that, then effectively you have a brain-activated switch, right? The application of that switch is then completely, can then be applied in any application. It's around the UI or the experience that you build around it. So if you wanted to do communication, which I'll show you shortly, you can do like a grid selection thing, just like yes or no, switch between them and use that switch to choose the option that you want. That's communication, yes, no communication. Very basic communication, but done, right? If you wanted to turn a light on and off, on, off, switch between them, use your brain switch, choose the option, you're done, right? So it's kind of that, getting to that point of that switch, which is what we're focusing on. Because once you have that, the applications are kind of endless in terms of what you can produce. Yeah, and so that's an example of a very active thought process. There are others that are more passive. So for example, using kind of like what I was talking to you before about Alzheimer's, how when you look at an image of a face, you get a particular spike. That can also happen when you're presented with visual stimuli, so like flickering lights. So if you look at something that's flickering at a particular frequency, as opposed to something that's flickering at a different frequency, your brain responds in 2 different ways to that, and that's also detectable. But in order for that to work, you need to have electrodes at the back of your head, which becomes a limitation for our user group who mostly have headrests. Because they can't move, their heads have to be supported, and so you can't put electrodes at the back, and that's kind of a limitation with our population. So we haven't looked at that way of doing things. But yeah, so there's kind of a range of ways of getting information out of the brain, and it's just figuring out what's more appropriate and what works better for whatever user group. Yeah. Did that answer your question?
Yeah.
Yeah. Okay.
So this device in particular, it reads just frontal?
Yeah, so this one just reads it from a single electrode on your forehead. So a single channel. And that's, you can't get any simpler than that, really. Ideally, we would like to have a few more so that we can get a bit more, I guess, confidence in the metrics that we're producing. But again, we'd have to look into hardware for that.
The pattern would be the same. It's just like have a fine-grained devices feed you with information. Like how having more probes would
Right.
help you.
So it's another. So because it's an electrical signal and it's only around the proximity of the electrode, what it means is if you have, say, a neuron that fires here, right? So this is on someone's head, and you have a neuron here that fires. It's going to look different at this electrode compared to an electrode over here, just because there's all these neurons around it, and on the way, it'll get contaminated with other signals, right? So having more electrodes in different places means you're getting more information and you're able to localize a bit more about what happened at this neuron in particular. And yeah, that's why. So more information is better because then you can start looking at more complex signals and actually breaking it down into finer components. So for example, like looking at if we had an array going across the motor cortex, we could look at individual limb movement kind of thing. Like whether someone moved their right arm versus their left arm and their right leg versus their left leg. You can start doing more sophisticated stuff like that. Yeah.
So I'm guessing like the amount of information that our brains process at a simultaneous like moment, right?
Yep.
You think one thing, there's a lot of stuff going on.
Yep.
If we had to compare all of that information coming out the brain to how fast we can compute that information, like is there a trade-off that you guys are making there? Because like you can't obviously handle all of that.
Yep. So the easiest, I guess, so we're not processing as much information as the brain, right? Because it gets.
So you're not cherry picking what you want out of that information that's coming.
Yeah.
through this.
Yeah, and also by the time it gets to this electrode, it's already been kind of aggregated already. So in terms of like individual neuronal activity, you've already kind of consolidated it into one signal. And so pulling out the information, you're just looking at what you want. You don't have to go through all of it. And then, yeah, so that process in itself is, there's a lot less going into the software than what's going on in your brain. But then the actual, so the other issues that you have is response time. So how much data can you collect as like a buffer or a window before you can measure an achievable or useful result? And then how much delay does that introduce into your system? So that becomes a bit of an engineering thing. But because our population typically haven't ever interacted with technology before, they're not used to the almost instantaneous effect of clicking your mouse or hitting a key. So it's okay to have a little bit of a bigger delay. So it doesn't have to be absolute, like, or hard real time. It can be a bit softer. Yeah. Yep.
You mentioned that training people who are using it. How long does that usually take? Process?
It's an interesting challenge. Because I talked a little bit earlier about how it's been used in research a lot, but because it's so new and no one's been able to quite get it going in the commercial space, no one really understands much about what the training should look like or what it needs to involve. And so we've done a little bit of work around that. And it's really interesting because at the university when they do a study, they'll just do like maybe come in, do this exercise once, and then that's it. Like it's very hard to do a longitudinal study where people keep coming in, doing it again, and go away and come back, and then repeat that as well. But based on our approach, most people can do something within a couple of minutes, like just get something going, or have a visible effect. Longer term, though, it takes. I think we've done trials of up to I think 10 sessions, each session being about half an hour, where they just practice doing different control activities, and by then there's no additional or not much additional improvement, I think, from what we've seen. But then the starting point is also very variable. So people who I think meditate or practice mindfulness often find it easier to start off with. Also people who play games, just saying. Yeah, generally find it easier to do the initial raising of focus or attention to get something to happen. The flip side, though, is that it then becomes a little bit, it's a little bit more counterintuitive to do the lowering of focus or attention, because you kind of have to distract yourself a little bit, and you can't focus on not focusing because that's focusing, kind of thing. So the process around that is quite difficult to pick up initially. The other thing is that with sort of focus, you don't have to think about the same thing. It's different between people as to what works and what doesn't. So, for example, Sav is quite a, oh no, she does math. So Sav does math. She just counts up in twos, and that works for her. I have to count backwards from like 1,000 intervals of 47 or something for it to work to me. Or I can do a visual exercise where I imagine an object, trace its outline in my mind. Some people can do it better if they're reading something or imagining music or songs. So it kind of varies between what works and what doesn't work. Yeah. Anything else?
Is there any sort of calibration process?
Yeah. At the moment, there is a need to calibrate. The process is still being figured out as to what works and what doesn't work. Just because, yeah, as I was saying, there's a lot of variability, and it does affect. So you do need to kind of tune it before each use, and it does change over time as well. So even within a session, depending on how long that session is, we've just never had a long enough session because no one can wear this for long enough. We haven't been able to figure out how often it needs to be calibrated or recalibrated, but because it is affected by things like mood and stress and all that sorts of stuff, it's hard to say. Yeah.
We've got about 20 minutes left.
2 minutes? Okay.
Yeah,
A demo. Okay. So can you all see the screen?
yeah.
Okay. So you guys probably working with software know like that the number one rule with demoing software is that it will break as soon as you try and demo it. Right?
You have to pray for the demo.
So I'm pre-warning you. Okay.
So this is the software that you guys.
So this is the software that, so this is Nous. This is the software that we've built, and it works as kind of a platform for different applications. And so in this case, what happens is it uses blink to change options, which is on the side there. So I've been blinking my eyes to just switch between them. And then it uses that green bar on the left. The progress bar is my current level of focus or attention. And so I used that before and it crashed. Interesting. And I used that before just to select this option. So there's a couple of demos here. One is this multi-choice, I guess, application, which is an example of how you could communicate at a very basic level. So kind of like taking that yes-no thing I was talking about before, but taking it a level further and providing multiple answers to a question. So instead of, say, asking someone, are you hungry? Yes, no. Are you tired? Yes, no. Are you sleepy? Yes, no. Are you in pain? Yes, no. More going through the process of how are you feeling, and then provide the options of hungry, tired, in pain, that kind of thing. So this is new.
Because you're not focusing on the application.
Maybe. I'll have to look into that later. But so, as I was saying, yeah, so I blink through it to switch the options. So I'm just blinking to pick one, and then when I get to one I want, I might try and focus. It's hard when everyone's watching you. So that was my option. Okay. So that's a very basic example of how you can.
So when you're blinking, then is it detecting between a deliberate blink as opposed to your natural blink?
There is a way. Honestly, I was testing it this morning and this didn't happen.
Do you need wide internet connection?
Maybe. What happens if I click continue? We'll see what happens. That doesn't matter. And so, sorry, what was I talking about? Blinking, right. Yeah, there is a way to differentiate between natural and intentional blinks. It just needs to be calibrated for that. And that's kind of one of the advantages of using this approach to detect blinking, because it is technically an artifact to a brain signal. Usually when you're doing analyses of EEG, electroencephalography, you want to filter out blinks. But in this case, we're using it as an additional control input. And so what that means is we basically have a two-switch system, where you use blink to do one thing and your brain switch to do something else. In the case where someone might not be able to blink or blink controllably, you'd replace the scanning with a timer. So it'll just switch through at a fixed interval, and then when it's on the one that you want, use your brain switch and select it. And so that's a single switch system. Cool? Okay. And so we were kind of building, so Nous is kind of like a platform. I hate saying platform because it's such a like a cliche term that software developers use. Everything's a platform, but I can't think of a better word at the moment. But so it's device agnostic, which means we can take this headset, any other type of headset made by another manufacturer, and plug it into this and do the exact same thing. The output is modular. So in this example, we've got a basic multi-choice communication thing. We also have a simple switch plugin that you can use to drive additional software via keyboard emulation. You can configure that to whatever the application is. So for example, like Spotify, you could configure it to media keys. There's also, we have plugins for controlling external hardware, like smart home technologies. We have one that plugs into Twitter, so you can tweet with it. And the other one that we've got as well, which is probably here, is a robot. And so the way that this was originally designed as just kind of like a demo thing, but we're finding it's quite useful as a training tool because people quite enjoy driving a robot with their brain for some reason. But yeah, so what it does is it uses the same control inputs that you would be using before to do something else. And in this case, it's your level of focus controls your acceleration or forward speed. Forward speed, it's two different things. Forward speed of the robot, and then blinking turns it. So if you blink once, it'll turn to the left. If you do a double blink, it'll turn to the right. I haven't driven it for ages, so I'm a bit rusty, but yeah. So if I blink once, it turns to the left. The wheels are in balance, so it curves to the right. If I do a double blink, it'll turn to the right. And so you can see there's quite a little bit of fluctuation in the signal, and that comes down to how you set. So when it's above here, it will move forward, and then the more above it is, the faster it will go. But yeah, so once it's below, it'll stop. And so yeah, that's pretty much it.
I can already see another application for the focus media thing, setting in meetings and collaborative.
Yeah, so
see who's focused and who's not.
There's a lot of people who have been wanting to use this in education, particularly with, like, control is one application of this. There's others in kind of like diagnostics, understanding physiology for treatment. Neurofeedback is a big thing. And so one of the, a lot of people do work with autism. And schools really want to use this kind of thing to monitor kids, to make sure that they're engaged and participating in class, which I think is cool if they can figure out how to do it in a non-invasive way. Then it'll be really, really cool. So that's pretty much what we do. So all of this is with the intention of, so our main purpose is around communication. We identified that as the most, I guess, dire need, purely because people who don't have access to communication then lose access to education, which then kind of sets them behind from the beginning. And so that was kind of the most urgent issue that we wanted to address. And the plan as we move forward is to branch off into other areas like interacting with the physical world, more applications, building more sophisticated algorithms to get more switches for control so you can do more things. And then, yeah, from there kind of go on to global domination and then multiplanetary domination. Yeah. Yeah, so if you want to have a go.
I think I'd say no.
The better device you could put on someone and then control them.
Yeah.
Going to the terminal realm here.
Okay, so you can pop that on. Get
I
your
want to see you reverse it, Peter.
Just the yellow bits out.
Yeah, on the yellow. Yeah.
Oh shit! Now you.
Okay. So it should go. Yeah. So try blink. Yeah. Try do 2 blinks. So do 2 distinct blinks. Oh, it's just signal quality. Yeah, it's fine. Here you go.
Peter can focus.
Not much. It's more Peter.
What's with you?
Your blink has to pretty much be slow.
Quite a distinct blink. Yeah. So this is probably a big distraction. Yeah, any other questions or things? Yeah, you guys can just keep, just cycle through and try it. Yeah.
What were you thinking about?
Literally nothing. No, just moving it forward. That was my.
Yeah.
It's such a weird feeling because you in your mind your language is the way you communicate, and now you have to literally just shut up and try and make this thing.
Yeah.
Put on.
Yeah, put it on so that it goes behind your ear. Yep. And that goes
And then
onto
I just think
on your
about moving
earlobe.
forward.
Yep. So what you want to look out for as well is make sure that this is green, because if it's not, it means you're not getting a good signal.
Yeah, it doesn't have a brain.
Brain not found.
Exception.
Dog.
404.
Might need to just give it a wipe.
Peter, you broke it.
Making my brain just so powerful.
So give your forehead a wipe, and then the electrode and your earlobe and the. Yeah. So what can happen is that during the day you can build up a little bit of oil or.
Here as well?
Yeah.
So does that electrode have to be? There's no lubrication or no sort of moisture between it that it can go.
Yeah, I mean you can get away with a little bit, but then at some point, then yeah, it's not going to be giving you a good enough signal to get any useful information outside. Yeah.
Mind if I record this or?
I do not mind. They're already recording it.
I don't want to get fierce.
You know, it's fine. So to meet, 1 blink is left and 2 blinks is right.
Titanic.
How do I reverse?
That's coming in version 2.0.
Is the robot got a
Stop
name?
it. Stop it. Stop.
It's hard to stop. Yeah. I've also set the threshold reasonably low as well, just to make it easier for it to move for you. But if you wanted to increase the threshold, it would be easier to stop. It would just be harder to start to move again, that's all.
Have you nicknamed the robot yet?
Sorry?
Have you nicknamed the robot yet?
Yes, it has a name. It is Cornelius.
Cornelius. What is good on there, little raspberry?
It's an Arduino based. So we didn't make the robot either. That's just an off-the-shelf educational robot.
Okay.
So I think it's got like an array of sensors and stuff. It's quite cool. But people can program it using Scratch, as well as Arduino. So it's mostly for kids.
Go forward, Sean.
It's not going forward.
Because you're not focusing. It's easy, dude. We all can blink.
Because you got to maintain the focus. Yeah, that black line is the threshold you need to get it above for it to go.
If you focus on that, it's actually more distracting.
Yeah. So it varies. Like some people like to look at the bar, whereas some people just stare at the robot the whole time. Yeah.
That's so cool.
What's the range of voltage of an impulse that is picking up?
Peak to peak is about between, I think, 10 and 100 microvolts.
10 to 100
Microvolts. So it's pretty small. So yeah, interestingly, one of the first toys that came out with this device was a collab between, I think, the company and Mattel, and they made a Star Wars Force toy. And you use that to, I think, levitate like a ball in a jet of air, and that was their toy.
So those sensors that they inject, the smaller ones that they inject,
So this is going to your toy.
they must have a lifespan to them as well. They can't like sort of.
Yeah. Currently, I think FDA rules mean that you can't have an implant in the brain for more than 3 months. So every 3 months, they have to cut their head open, take it out again, which is crazy. So
What's earrings and thing?
earrings, like earring holes or the earring itself. You probably want to take the earring out.
No, it's fine.
That's pretty cool, actually.
It's more of an effort to take this earring out and put it back.
That is cool.
She's already gone.
You didn't tell me.
I tried to tell you everything.
Now you have to get
Jeez,
everything.
I know you want me tour, but okay, I have to tell you everything.
You didn't tell me. He was signing up, and I was like, "Oh, are you here for the Bravo?" And I was like, "Are you James?" Oh. He's like, "You let me know."
So I'm guessing going further, like having all sort of sensors across the whole brain.
Yeah.
There is, I guess there's like tolerance. Like you said, there's a general thing of how to focus. There's this sort of frequency that you focus on. With the more sensors,
Yeah.
I'm guessing you can tweak that
Yeah.
more.
You can tweak it more, and you'll also you'll have more. What's the word I'm looking for?
Distinguish.
More samples. So like kind of like how when you sample sort of data, you try and get as many as you can before you kind of like get an average or whatever, and that helps to build confidence in what your outcome is. So in this case, we only have one channel, and so we're everything depends on that single channel. But if we had two channels and they were saying the same thing or similar things, then that gives more confidence in whatever result we calculate or produce. So it's kind of similar thing, yeah.
So your data going forward can actually be quite valuable. Once
Yeah.
the data actually gets-
That is kind of like a whole other issue is if this gets out there and we start collecting a lot of brain data, then that is a very useful resource for different organizations and people, especially with our population as well, because it's not a population that is accessed often. Like you don't see people who have such severe levels of disability out in public often because they're confined to their homes or whatever environment, and they don't, and so you don't see them. And as a result, they're kind of like a little bit underserviced population, if you will. But yeah, stuff like this kind of getting to them will help us get information out of them, basically.
Considering, yeah, that actually be useful. Like considering, do you think like Stephen Hawking used infrared?
Yep.
It's cheap. They're cheap, I suppose. Thousands and thousands. Like considering the gear here is 200 for the headset.
Yep.
But you can wire out.
Well, Stephen Hawking had a dedicated team from IBM build his system for him. Yeah.
Wow. Okay.
So his that's why he's a very unique case. Like he's often used as an example, but there are many other people like him who don't have access to that kind of level of care and technology, and so that's kind of, I guess, the kind of message or thing that we want to get out there is that there are millions of people like that, like him, who don't have that custom-made system, but could still potentially get a lot out of being able to communicate and interact with the environment, right? So that's kind of what we're trying to do.
And now, in terms of like next steps, what is the main focus that you guys are focusing now?
So the main step now, so right now, this is kind of working on in the background. We're trying to solve problems around perception of the technology and teaching people how to use it, especially therapists. So therapists would be the people who would be going out and taking the system to people and setting it up for them and teaching them how to use it. And so we need to make sure that they're comfortable with it, which they're not at the moment. So we're doing a lot of work around trying to understand why they're not and what we need to do to make it so that they are.
And is it comfortable with just using it, or
yeah.
they're reluctant to I don't want to try? Or?
I think a combination of both.
Okay.
So it needs to be easy enough, like on the surface, that they're like, oh, I think I can use that. I can see myself being able to set it up and go through the process. And then the other thing is being like, it sounds kind of scary. How do we make it less so, and what can we do so that when they do use it, they have to do as little as possible. Basically, like just put it on, click a few buttons, and they're good to go. If something goes wrong, it tells them what's wrong, and they just need to fix it. As opposed to them being like, oh, there's a poor signal. Maybe it's the battery, maybe it's the connection, maybe it's the Bluetooth thing, maybe it's the software, maybe it's the hardware. Which is why getting into hardware would be really good for us, because then we would have control over the whole process. It's like right now, we only manage the software. So once you get the device and put it on and get it going, after that, that's all us. So we're doing all the interaction and the onboarding and all that. But before you get there, the issues with that, we can only do so much with the headset.
You're limited to the hardware there.
Yeah.
Wow.
Yeah.
So you're talking about like buffering and stuff. You use this technique on this device, like to like.
Yeah.
Is there a signal? Or?
Yeah, there's a signal. So as I said, the raw signal looks a lot like an audio signal, and so you take samples of it, you window it, whatever, convert it into frequency domain, and do all sorts of analysis on it.
Is it in scales of seconds or? Like?
Yeah, about a second would be the maximum at the moment. Yeah.
And that doesn't vary from person.
No, that's consistent.
So you need to be able to hold this
Yep.
signal for.
Yep. So in the multi-choice thing that I did to choose options, in order to actually select it, you have to raise the focus and then maintain it for a period of time, and then once you've done that, then that's when it activates.
I always bring it back to coffee.
Oh, wow.
Where are you going, Jim?
Because in case you go try and get other means of, as you said, the people that don't always have the ability to move, to function like that. For example, someone that's had a stroke, they don't really have full movement of their face, like going after like a micro expression is probably not
Yep.
an accurate enough sort of way of determining it.
Stroke's an interesting one, because you, depending on how or where the stroke happens, you have different effects on brain function. So we haven't yet tried with the stroke population because we just don't know enough about it yet. But it will be something that we will look into because it definitely would be useful for especially in the areas of where there's limited movement. there's potential to get in on there as well, because we're not just focusing on brain activated stuff anymore. We're kind of also looking at other types of assistive switches that are based on this kind of similar technology and principles, using biophysiological potentials, which is like electrical activity. So yeah, it's kind of sort of like branching out a little bit in terms of what we're exploring as possible solutions, because this is really, in its current state, this is worst case scenario, where you can't use absolutely anything else, and so you'd have to use this. But there are checkpoints before that which are possible, which also don't exist, which we could do. So thinking about that, yeah, needs to be more on your forehead. Yeah. Nope. So it's not very comfortable, eh?
No.
Did anyone find it comfortable?
No.
You found it alright? But you only wore it for like 5 minutes, yeah.
So did any of you like find it throbbing? You had it on for a while. Did you feel anything?
No. That's because you're focused more on the robot.
You're filled with adrenaline and endorphins with the driving the robot, that you're not worried about the pain. So give your forehead a white and the earlobe electrode in. Yeah.
Brilliant, James. Thank you.
Oh, no worries. Thanks for coming. Thanks. So yeah, next stage is to get a electric wheelchair and do a similar thing with that.
Yeah. Just put reverse in it.
Yeah, reverse.
That would be ideal.
Reverse needs to be.
Like drag cars and stuff.
Yeah. So if MYOB wants to sponsor us an electric wheelchair, we can do that.
Are there any other headgear sort of things on the market?
Yep. There's quite a few that are coming out now for mindfulness, and targeted towards like elite athletes in sport. So the form factor that they come in are like headphones with the electrode array on top. They cost like $500, $600 US. There are other ones similar to this which have a slightly different physical configuration but similar underlying hardware. And then you start to get towards more researchy type things with like caps, low cost caps, which are around sort of 8 to 10K, and then start going more and more into more sophisticated research equipment. Yeah, but I think like we really want to build our own.
Is it the hardware in there that's the issue, or just the one?
Both. So firstly, the physical form is not usable, but then also there's a little bit going on in the hardware that that's closed off to us, because it is a like how they filter the signal.
Is filtering done?
There is some onboard filtering. I don't know exactly what it does, but for me personally, having less knowledge about what's going on makes me uncomfortable, because I want to know what's happening and to be able to understand it properly to improve it, or if something's not working. But yeah, so we don't know exactly everything that's going on with this, but it's just something you have to deal with. Sorry?
Have you opened it up?
Yeah, I know what's inside. I did that. Took it apart and looked at all the components. I actually gave one to Kyle as well, I think. Has he taken it apart?
I haven't seen him taking it apart.
Okay.
I'm keeping it.
It doesn't work, so you should take it apart.
Would
Yeah.
you know what other people are using this for?
So most people who seem to like buy these devices and use them are like hobbyists or like makers who get it, do a little project, and then that's it. Like around sort of mindfulness or game, like a small game, or meditation. Not many people use it for control, like us. So but yeah, it's like there's no kind of mass market thing like this coming out or anything. I think people are still trying to solve problems of usability and how to make it appealing. Yeah, because it's an interesting area, but not everyone's cracked it yet, which is kind of good for us in a way. Yeah.
Cool. Guys, that's time.
You guys got to go back to work.
Question, clip for the ear.
Yeah.
James, thanks for
Is that the switch?
sharing your story and
No.
it's cool stuff with us. It was really
No worries.
interesting.
Thanks for having me.
Yeah, shake hand first.
Cheers.
Got a lot of NYBT
Oh.
shit for you.
Cool.
You can join us. And,
Thank you.
Yeah, thanks again.
No worries. Thanks for having me.
Cool talks.
Yeah.
So we've always got some cool topics coming up later in the year as well. So you guys got time to come through. Let's learn together. Cool. Thanks, James.
No worries.
Thanks.
Does the sensor in the front detects the frequency? What is the...
So this is a reference. So if you